Okay, here we are in quiz 11, and we want to talk about some Euler circuits and Hamiltonian circuits today. So the first question is decide if an Euler circuit exists for the graph. In order for an Euler circuit to exist, I need to check two things. And if you look at the Euler circuit language, it's an if and only if statement, right? This is a very strong definition. I need it to be connected, and I need every vertex to be even. So the graph is connected. I can move from any point. If I picked a point, I can move to any other vertex on the graph. So that's a check when I check this characteristic. Every vertex is even. Let's count. This is degree 2. This one is degree 4. This is degree 2. This is degree 3. And this is degree 3. So these two of degree 3 means that it fails this second test and that there's no Euler circuit here. Problem 2, determine if the path given, and that path is A, D, C, B, E, A, is a Hamiltonian circuit. So for it to be a Hamiltonian circuit, I need it's a circuit, right? It starts and ends at the same vertex, and I hit every other vertex exactly once. So let's maybe color these vertices as I go through them. So I start at A, here, and then I go here to D, to C, to B, to E, and then I go back to A, which is along this path, not back to C, but back here. And I start again. So this hits all 5 vertices, and it doesn't repeat any vertices, so yes, this is a Hamiltonian circuit. Problem 3. Again, I want to determine if the path is a Hamiltonian circuit. So I'm going to look, and the circuit should be, or the possibility is, F, B, D, A, E, C. Now you can look right here, and we'll maybe do this same thing. These does not have the same starting and ending point. I start at F and end at C, and that's going to be a problem. It's no longer a circuit. I think I hit F and B, D, A, E, C. I hit all of the vertices, but it doesn't go back to my same starting point. At the starting point. So no, it's not a circuit. Problem 4, determine whether the graph has a Hamiltonian circuit. And there were these 3 principles. You probably got the sense that this is a less sure way of testing. It's possible for it to fail these tests, but let's check principle 1. I think is the one that is going to work here. So principle 1 has a few tests that I need to make sure. It has to be simple and connected. We want to test and see if that's true. 2, no loops. 3, has n vertices. and n is greater than or equal to 3, and for the degree of each vertex is at least n over 2. So let's go through these step by step. It is a simple graph. I don't have any parallel edges, and it's also connected. So it matches and meets this first criteria. There are also no loops here. N vertices, the number of vertices I have is 6, and that's bigger than 3, so yes, it meets that. And the degree of each vertex is at least n over 2. That in this case is 6 over 2, which is 3. So let's go back and make sure the degree of each vertex is at least 3. So here I have degree 3. Here I have degree 3. Here 3, 3, 3, 3. It matches this criteria too. So yes, it should have a Hamiltonian circuit. And honestly, it's not that hard even to find a Hamiltonian circuit here. Like, let's say if I start at this point, I can go up, down here, across, up, down, and back over to my original starting place. I hit all 6 vertices, and I don't hit any of them more than once, and I begin at the same place that I ended. Problem 5, is the graph bipartite? Meaning, can I color it with just 2 colors? So let's just start with a couple colors. I'm going to color this vertex blue. And then I want to move, and so the points that are adjacent to that I'll color red as long as they're not adjacent to each other. So that one's red. This is another adjacent one, but it's not adjacent there, so I can color that red. This is an adjacent vertex, so I can color that red, but it's not. So I have that. Now I want to switch back to blue, I believe. That's fine. That's not adjacent to my original. Or this one. Let's see, I think I can also color this blue. And I can get, finally, one more red in here. So yes, I can color it with 2 colors. So yes, it's bipartite. Problem 6, determine whether the graph is connected or disconnected. And you can see this is a very visual idea. Here I have this point, blue, and let's say I want to try and move to this other point, red. For it to be connected, I have to be able to get there. But the only edge moving from this vertex is over here, and I can't get to this red vertex. So this is the idea of a graph being disconnected. There are some vertices which are literally split from other vertices, and you can't move to them along an edge or a series of edges. Problem 7, determine whether the sequence of vertices is a simple path, a closed path, circuit, or simple circuit. So I have this sequence B, F, G, C, D. So I want to just go ahead and map that out for you guys, and then we'll talk about which one it is. So here I start here. I think that it's going to be one of my paths. It's not a circuit because I don't begin and end at the same place, right? That is what I need to have in order for it to be a circuit. So for it to be a path, the difference between a path and a simple path is that I can repeat edges and vertices in paths, but not in simple paths. So we're looking for repetitions here. So here, this one moves from B to F to G to C to D. So I don't repeat any edges or vertices, so I believe the answer here should be that it's a, oops, let me get an actual pen, simple path. Okay, 8. The question reads, use Flory's algorithm to find an Euler circuit for the graph beginning and ending at A. So here I start at A, and I want to move along this path, and I think all of the multiple choice options move to B. So once I move to B, I erase this path, and it's no longer a part of the graph. Okay, so then I move to this I have step 1, oops, and this is step 2. And I'm here in B. Okay, now from here I can move, and I believe the multiple choice options go to C, so once I do that, I'll erase this one as well. Okay, then I move to D. The only choice now is to move to D in Flory's algorithm. And I erase this path from C to D. To move from D to B. So this one, let's see. This is step 4. And go back here, step 5, and I think I'm going to come here for step 6, and finally here for 7. So but let's go. A, B, C, D, go back up to B, I erase again. Then B to E, I erase again. I hit E. And then up here to A. So I've covered every single edge. I've only covered them once. I hit B twice, which is allowed to hit a vertex twice. But this path should be the path A, B, C, D, B, E, and back to A. Problem 9. What is the minimum number of colors necessary to color the graph? Again, I'll pick a starting point and then begin coloring from here. So here I have, let's say this in red. And then the adjacent vertices need to be colored a different color. This must be blue. This must be blue. And let's say this one is blue. That's good, none of those. This one can be red. It's not adjacent to anything. But now C cannot be red or blue. It has to be yet another color. So I get 3 colors here in this graph. Finally, 10, what's the length of the given path? Which really you don't even need to see the path, to see what this is, CFGDC. And you can tell even just between these letters, between each one is an edge, which gives you 1. So from here to here is 1, 2, 3, 4. It should be 4. And the same if you're visualizing this on the graph. There's 1, 2, 3, 4. Okay, let me know if you have questions.